Hello everyone, this is Dr. Hopkins with our next video. Here we're going to address more measurements, including density, a specific measurement, and then talk a little bit about accuracy and precision. So first, let's define accuracy and precision in terms of measurements. So accuracy, and sometimes these two terms, accuracy and precision, get conflated. So you need to make sure that we're on the same page. Accuracy is how close a measurement is to the true value. So if there's a known actual value to the measurement, how close we are to that, how close we are to being correct, if you will, is what accuracy tells us. Precision is how close a measurement is to another set of measurements, or how close a series of measurements are to each other. So how good is our measurement? Do the measurements give you consistent values? And so actually precision is related to, we talked about in one of the previous videos, the uncertainty of a measurement. So it tells you how uncertain is our measurement is related to a precision, so we can statistically evaluate that. Okay, so density is and everybody should know what this is, but it's a fundamental property of a substance. So the density of solid ice or the density of pure iron or copper will always be the same given constant temperature and pressure. Okay, and it doesn't matter where you are. You could be on Mars, you could be on Earth, you could be on Jupiter, and the density of that material is a fundamental property of the material. And mathematically, it's basically the mass per unit volume. Okay, so I write the equation here, density, we usually use rho, that's what that is, that Greek symbol is equal to the mass per unit volume. If we were keeping track of SI units, we would write the density in kilograms per liter, because mass, the SI units are kilogram, the volume, the liters are, or the SI units are liters or decimeter cubed. But most of the time for chemistry, we're going to do grams per milliliter or grams per cubic centimeter. And here I have a table with a few kind of common densities, or densities of common substances, like ice is 0.92 grams per milliliter. Water at 4 degrees Celsius actually is exactly 1, and so forth. And you can see where air is less dense, etc. So the nice thing about density is it gives us another chance to do some calculations, and some unit conversion. So we can do a little math here. And so we've got a problem where we've got 0.01 decimeter cubed, which is a unit of volume, okay, cubic side lengths. It has a measured mass of 78 grams. What's the density in grams per cubic meter? Or cubic centimeter, excuse me, not cubic meter. And then, so we would write 78, so we need mass per volume, right? If we go back to our equation, so this is not a density, so 78.0 grams divided by 0.010 decimeter cubed. Now we need to convert decimeter cubed to meters cubed, or excuse me, I keep saying that, centimeters cubed, so we got 1 decimeter cubed. And then there are 1,000 centimeters cubed, because there are 10 centimeters in a decimeter. And then we have to cube that, so 10 times 10 times 10 is 1,000. And then we need to plug all this into our calculator, divided by 0.01, divided by 1,000. And we're left with a density of 7.8 grams per cubic centimeter. And that's how you would do that math, that conversion. And I did want to show how to do those kind of cubic length measurements or conversions for volume. And then let's do another one if we have 25 cubic decimeters. So this is the same thing, by the way, as a liter of air, has a mass of 0.032 kilograms, so we want it in grams per cubic centimeter. So our mass over volume, so our mass is 0.032 kilograms, and then I'll divide by our volume that we're given. Okay, And then we need to do some conversions. So the first thing we're going to do is we're going to convert kilograms to grams. So there are 1,000. So if we were to go back per kilogram, grams per kilogram, okay? So that basically, if we want to cross them out, the kilograms are going to cancel. And now we need to go from decimeters cubed to centimeters cubed. So we have 1 decimeter cubed per 1,000 centimeters cubed, okay? And so now that cancels that, but our 1,000 and 1,000, so basically we just divide our 0.032 divided by 25, so 0.032 divided by 25 is 0.00128 grams per cubic centimeter. Okay, and I probably have written too many significant digits because you'll notice this number has 2. So if we were to do this in sig figs, 0.13 grams per cubic centimeter. And so that's some examples of some calculations. Now we want to look at this in terms of precision and accuracy. Let's do the same kind of calculation and let's figure out how precise. So let's say we had 10 milliliters of ethanol and we measured the mass 3 times. And we calculate the density. So the density is, let's get our pen back, mass per volume. So it's, for one of them would be 8.1 divided by 10 milliliters. Now we don't have to do any unit conversion because everything is already in grams and milliliters. And we're left with 0.81 for the first one for our density. It's already got the units up here in the column. And then this one would be 0.75, and this one is 0.82. So the average is 0.81 plus 0.75 plus 0.82. So we would just take the average of those two. So 0.81 plus 0.75 plus 0.82. We divide that by 3. And we're left with 0.793, okay, which to the number of significant digits is 0.79, and I should put units on there, grams per milliliter. That is our average density, okay. The actual density is 0.79 grams per milliliter. So how accurate is it? Is we're exact. So there's 0 grams per milliliter difference in our accuracy. And then we want to look at how close each of the measurements are to the average. So this is accuracy. This is precision. And the first one is what, 0.02 away. So the difference. So actually what I should do is say 0.81 minus 0.79. We're subtracting each value from the average. And so you get 0.02. And then if we get 0.75, subtract 0.79, but take the absolute value, we get 0.04 and then 0.03. I don't have enough room down here. So those are our 3 precision values. So our measurements were all